Good morning. Hello everyone and welcome back to the channel. In today's session, we dive into one of the most important developments in modern cryptography, the NIST SP 800-232 standards and the Ascon family of lightweight cryptographic algorithms. Now you may ask, what makes Ascon special? Well, traditional algorithms like AES and SHA-3 have been the backbone of secure communications for decades. They are rock solid, widely trusted, and deeply embedded in the compliance framework. But when it comes to tiny resource constrained devices like the IoT sensors, the medical implants, telecom edge modules, or even handheld banking devices, AES and SHA-3 are too heavy if no hardware accelerators is present. This is where Ascon comes in. Designed around a compact 320-bit permutation, Ascon provides authenticated encryption, hashing, and extendable output, all optimized for software only microcontrollers. That means lower energy use, smaller code size, less RAM, and better performance on the very device that are shaping our interconnected world. In this video, we'll explore what lightweight cryptography really means in practice. We look at a detailed comparison of Ascon versus AES SHA-3, looking at performance both on software only microcontrollers and on devices with hardware accelerators. We'll do a breakdown of the four Ascon variants, the AED 128, the hash 256 and XOF 128, and the CXOF 128, and when to use each one. Real world relevance across BFSI, telecom, IoT, and healthcare we'll be looking at, where crypto agility is no longer optional but a necessity. Most importantly, we will simplify tough concepts like nonce, tag, and digest security levels into everyday analogies. So, whether you are a student, a practitioner, or a technology leader, you will walk away with clarity and confidence. That's the expectation. So, let me try on this today. So, join me as we unpack this fascinating shift from traditional cryptography to lightweight cryptography and discover why Ascon, the winner of the NIST lightweight cryptography competition, is now officially part of our security toolkit. If you are already there and ready to understand how tomorrow's device will stay secure with less power, less memory, and equal strength, this video is for you. This is your host, Savit Vittal Salian. Stay tuned and let's get started. Namaskar. The agenda. In August of 2025, the National Institute of Standards and Technology, or NIST as we know, released its special purpose 800-232, finalizing the Ascon family of lightweight cryptography standards. Ascon provides authenticated encryption, hashing, and extendable output function designed specifically for resource constrained devices such as the IoT sensors, the embedded controllers, and low power medical or telecom devices. The Ascon family gets its name from its technical design. Authenticated encryption with sponge construction, the AES and the CON, or in short, Ascon. It reflects both its function and its lightweight sponge based structure, which made it stand out in the Caesars and NIST lightweight cryptography competitions. Ascon was originally submitted by a team from Graz University of Technology, Austria, and collaborators to the competition for authenticated encryption, security, applicability, and robustness competition. Its full submission title was Authenticated Encryption and Hashing with Ascon. What's the meaning? Well, Ascon is short for Authenticated Encryption with Sponge Construction. It reflects the fact that all Ascon algorithms are based on a sponge construction built over a small 320-bit permutation. The name was chosen to highlight both its everyday focus and its sponge based design in the same spirit that KISAC or SHA-3 reference its unique structure. The design philosophy embedded in the name is the AS prefix ties to the AED, which is the authenticated encryption with associated data, and the con suffix comes from the sponge constructions, as in case in SHA-3, but with a smaller, lighter state. So essentially, Ascon is the AEAD plus sponge construction. Adoption into the NIST SP 800-232. Well, Ascon was selected by NIST in 2023 as the winner of the lightweight cryptographic competition and then standardized in 800-232. NIST kept the name Ascon unchanged to preserve continuity with its well studied literature and open source ecosystem. Let's look at the sponge construction. Well, a sponge construction is a way of designing cryptographic algorithms that process data in two phases. The first phase is the absorb phase. In this, the input data is first soaked up into the internal state. And the phase 2 is squeeze phase. The algorithm squeezes out the required output. Think of it like sponge in a water. You dip the sponge into the water, it absorbs the water. Then you squeeze it, the water comes out. In cryptography, the input is where the water you pour in. The state is the sponge itself. And the output is the water you squeeze out. That's the analogy. So, how it works in Ascon? Well, Ascon's internal sponge is a 320-bit state. The data is fed into this state. The state is repeatedly permuted, like mixing the sponge. And next, the output bits are extracted or squeezed out for either hash, tags, or random looking bits. So, why sponge? Well, sponge is flexible, compact, secure, and streaming friendly. When you say flexible, it's the same design, can do hashing, it can do encryption, or it can do XOF. It's compact because one permutation core is used for multiple functions. It has a smaller code size. It's secure because security depends on the state size, the capacity, and how much data is absorbed at a time. You can process the data in chunks, which is useful for IoT sensors where we have very little RAM. Analogy? Well, imagine a tea bag as a sponge. You dunk it, which absorbs the hot water and the tea leaves mixes. You squeeze the bag, flavored tea will come out. Depending on how much you squeeze, you can get short or long output, just like XOF, which is extendable output function. In summary, a sponge construction in SP 800-232 means a cryptographic design where data is absorbed into fixed size states and then output is squeezed out. It gives Ascon its simplicity, flexibility, and efficiency, making it suitable for lightweight devices. What lightweight means in the context of Ascon family of lightweight cryptography standards? Well, lightweight is not equal to weak. Lightweight does not mean reduced security. Ascon is designed to deliver a 128-bit security strength, which is comparable to AES 128 and SHA-256, but in a way that is more practical for resource constrained environments. Let's look at dimensions of lightweight in Ascon. NIST uses lightweight to highlight efficiency across multiple resource constraints like code size, like small footprint in softwares. Ascon's permutation uses only simple bitwise operations. This allows implementation to fit into a few kilobytes of flash or ROM. These are important for devices with limited storage. Example, the 38 KB microcontrollers which are used in IoT sensors. From a RAM usage perspective, Ascon's internal state is 320-bit, far smaller than SHA-3's, which is around 1600-bit state. This low RAM requirements allows cryptography on devices with just a few kilobits of RAM. From an energy consumption perspective, it is designed for battery powered or energy harvested devices like your wearables or implantables or smart cards. With a lower cycle counts in pure software translate to reduced power drawn compared to the AES GCM or the SHA-3. From a CPU performance perspective, it works efficiently on a 8-bit or a 16-bit or a 32-bit processors with no dedicated crypto acceleration. Unlike AES, which often benefits from specialized instruction or hardware engines, Ascon is tuned for general purpose microcontrollers. Ascon, if implemented in a hardware, Ascon cores are tiny. So there is a simplicity in the hardware, nothing complex required when you have Ascon used. This makes them attractive for RFID, SIM cards, embedded controllers, where silicon area and the cost are tightly controlled. So why NIST standardized Ascon as lightweight? Well, many IoT or embedded devices cannot afford the memory or the power or the silicon cost of AES, GCM and SHA-3. Ascon fills this gap by giving such devices modern cryptography that is secure, efficient and versatile. Simple analogy, think of AES SHA-3 as a SUV. It's powerful, secure, reliable, but are heavy and fuel hungry. Whereas Ascon is like a compact hybrid car. It is still safe and reliable, but it's optimized for tight space, less fuel usage, and lower cost. In SP 800 232, lightweight means optimized for constrained devices, reduced cost size, RAM, reduced energy consumption, lower hardware cost, while still delivering a robust modern security. Let's look at traditional versus lightweight cryptography. Well, traditional, which is AES or SHA-2-3, they are built for general purpose IT systems, which are servers, PC, mobile phones, and so on. They are optimized for high performance with ample memory, ample power, and often having hardware accelerators within it. They are prioritized throughputs and broad compliance over minimal resource use. Whereas the Ascon family is the lightweight cryptography here is built for resource constrained environments like the IoT sensors, the embedded devices, the wearables, the smart cards or devices on similar lines. They are optimized for low memory, limited code size, and for efficient energy consumption, as the energy source would be much lower as compared to the traditional. They prioritize efficiency and compactness. Do note, in the traditional they prioritize throughput. In this they prioritize efficiency and compactness while still maintaining the 128-bit security strength that you get from the traditional. Let's look at characteristics comparison. When it comes to core, the traditional has 128-bit block cipher in AES or a 1600-bit keysack permutation in SHA-3. Whereas in lightweight, it is a 320-bit permutation. When it comes to operation, AES uses SBOX, Xbox lookup. SHA-3 uses the 1600 bit state update, whereas lightweight uses the simple boolean operations, XOR and rotation, etc. The code size is between 2 to 3 KB. whereas in Ascon it's 1 KB total. The RAM need would be greater than 1 KB of RAM, whereas in Ascon is few hundred bytes of it. The hardware footprint, it's about 10 to 20,000 gates required, whereas in Ascon core it requires between 4 to 5,000. From a performance perspective, traditional are extremely fast as they use hardware acceleration, whereas the lightweight, they are optimized for software only MCUs, which could be MCUs such as Cortex M, AVR, or RISC-V. We look at this in detail as we move forward. Now, what is software only MCUs? But what is MCUs in first place? MCUs are microcontroller unit. A microcontroller is a small low power computer on a chip. It typically includes a CPU, a little memory, and basic peripherals. These are used in the IoT sensors, smart meters, wearables, medical devices, and etc. So now when you look at your smartwatch, there is an MCU in it. If you have a body sensor, a ring to take care or get your health stats, there is an MCU inside it. Now you know. So let's look at from a hardware and a software cryptography perspective in MCUs. Well, many bigger chips have hardware accelerators for cryptography. Example, AES engine or SHA module built into a silicon. These accelerators makes AES, GSM or SHA very fast and energy efficient. Whereas software only MCUs don't have such crypto hardware. All the encryption, hashing, and authentication must be done by the CPU alone using instructions like XOR and or rotate. As an example, this makes algorithms like AES much slower and more energy hungry in these devices. So AES and SHA-256 are not used in wearables. They need specialized modules. Now that is also possible. Example, in phones, you would have an accelerator. But if it is a low end device where an accelerator can't be put in because of the size and the energy requirement that is required to process, AES can't work as efficiently. It will work, but it will not be as efficient to your expectation, or the intention of the objective of that devices is defeated if you're using AES there. Why it matters for Ascon? Ascon was designed to run efficiently on software only MCUs. It's a 32-bit permutation, uses only simple bit operations that all CPU supports. There is no lookup table or multiplication in big finite fields like the AES. They need it. The code size is about 1 KB. It fits in a very small flash. The RAM usage is few hundred bytes, which is ideal for tiny IoT chips. That's why NIST calls Ascon lightweight. It runs well without needing any specialized crypto hardware. Example of software only MCUs. The ARM Cortex. These are entry level IoT microcontrollers or basic chips. The MCUs with hardware are like STM32 MCUs with AES engine, or the NXP's series with cryptographic accelerators, or secure element smart cards with dedicated core. These are examples. Simple analogy, think of MCU as a kitchen. With hardware accelerator, you have a, it's like having a blender, a food processor, a toaster, which are fast, energy efficient. Yes. Software only MCUs, well, you only have a knife and a cutting board. Everything must be done by hand. So there is no food processor, there is no blender, there is no toaster. With basic tools, you have to work. So Ascon is like a recipe that only needs a knife and cutting board, while AES often assumes you have a blender in the kitchen. I hope this helps with a little better perspective. A software only MCU is a microcontroller without built in cryptographic hardware. All crypto must run in software on its tiny CPU. Algorithms like Ascon are optimized for this environment, unlike AES SHA, which performs best with an accelerator. Let's look at a performance checklist between AES versus Ascon. AES or Advanced Encryption Standards uses block cipher as a block 128 block or 128, 192 or 256K bit keys. It requires additional modes for AD. It has a strong global adoption and compliances to various standards like PCI DSS, TLS, and so on. When it comes to Ascon, which is 832, 232, it's a family of lightweight algorithms constituting AD 128, hash 256, X of 128, or CX of 128. It's built on a 320-bit sponge-based permutation. It is designed for software efficiency. From a performance perspective, AES is slow when it is pure software. It has a high energy cost and shortened battery life. Do note this is software only MCUs. Okay, performance on a software based MCUs. AES is slow, it requires high energy cost and its battery life is low. It requires a large code size. It is RAM intensive due to lookup tables that is required for AES. Whereas when you look at Ascon, when it is on a software only MCUs, it's actually optimized for software only CPUs. It has much lower cycle count as compared to AES in pure software. It has a very small code size, which is 1K less. It has minimal RAM usage and thereby has an extended battery life, specifically useful when it is devices which are wearable or IoT types. Do note this is for AES and Ascon running when the MCUs is software only. Now when we take the same thing when it comes to MCUs with hardware accelerator, things change. AES, which was slower in software, when it is hardware based, it is extremely fast. It is energy efficient due to the offloading of to the hardware. Widely validated. And the ecosystem support is mature. We have enough libraries, drivers, certification, and so on when it comes to AES on a hardware accelerator. But when we look at Ascon, it is still efficient in software, but At this point of time, there is no hardware acceleration available. It's in development, tests are going on, experiments are in play, but no commercial at this point of time is known. Hardware support is emerging. It has a niche validation ecosystem. It's a new standard, still in adoption phase. From an energy consumption perspective, when it is AES running on software only, it requires high energy per encrypted byte. It's not ideal for, say, coin cell powered item. What is coin cell? Well, if you remember, your watch requires a cell, a battery which is coin shaped, the small ones. When you're running AES, it will just drain your battery that much faster. But when AES is on a hardware accelerator, it is much more energy efficient and often better than Ascon in this setting. Now, coming on to Ascon, when it is running on software only, it is energy optimized, competitive for IoT sensors and wearables. But when Ascon runs on hardware assisted, well, at this point it is promising, but with limited adoption. It's not yet mainstream, so we'll have to wait and watch how things move in that direction. So that's from a energy consumption perspective. The traditional higher energy draw in software only mode, bad for coin cell batteries. Whereas the lightweight part has lower cycle count, hence longer battery life cycle. Feasible on passive or energy harvested devices. So when you say traditional, that's the AES one. When you say lightweight, we are talking about the Ascon family. From a security perspective, AES has 128, 192, 256 bit strength. Ascon has 128 bit strength. Explicitly analyzed for nonce, misuse, and multi-key settings. We'll discuss this in detail as we move forward. But if you look at from a bit strength perspective, Ascon is in line, if not completely, but it's still in line, good enough protection from a security perspective. Not far behind. So traditional AES has security strength of 128, 192, 256. It has SHA with security levels up to 256. It's well studied and has a big global adoption. Ascon is a 128 bit strength. It's comparable to AES 128 or SHA-256. It explicitly guarantees in single key or multi-key and nonce misuse settings. It offers AED hash, XOFs from the same permutation, consistency across functions. We'll discuss this as we move forward. From a compliance perspective, AES is required in many compliance regimes, like the PCI DSS, TLS, banking. AES is mandated in many places. Ascon, though standardized by NIST, the compliance uptake is still early. Eventually, it will come in with the adoption of it because it's more practical for small devices. Well, traditionally, AES and SHA-2, 3 are mandatory in many compliance regimes. It's supported in almost every chip, HSM, and security library. Whereas Ascon is a new standard. It's approved by AED, approved for AED, hash, and XOF, but ecosystem is still growing. It's not yet mandated in compliance standard, but ideal for IoT or embedded deployment. Hence, it's only a matter of time then this also becomes a certain standard made as mandatory. It's more practical for those devices, especially the medical equipments. It's a matter of time, that is what is expected to come first. But let's see how things move. So the best fit scenario, AES with hardware or hardware accelerators, is best for banking, data centers, smartphones or higher end telecom servers, etc. AES on software only, it's impractical for MCUs without accelerators. Ascon software on software, it's best for IoT wearables, medical implants, sensors, or any other wearables that you have. It's best suited. Ascon with hardware, well, wait and watch. Future fit options for constrained devices once silicon adoption grows. At this stage, it's wait and watch scenario. Eventually, it might come in with developments happening in the silicon space. We might have an Ascon implementation with hardware on wearables, keeping the wearable reasonably sized, energy consumption being managed out. But at this stage, it is wait and watch. From a sectoral fit perspective, well, traditional best fit in BSI data centers, enterprise servers, TLS sessions, cloud platforms. When we talk about Ascon or lightweight cryptography, it is best for IoT meters, wearable health devices, SIM or eSIM modules, telecom edge nodes, point of sale terminals without the AES hardware. Analogy? Well, traditional crypto is like SUVs, powerful, compliant, reliable, but heavy and resource hungry. You can take the lightweight crypto as a compact hybrid. While it is equally safe, but it is designed to be energy efficient and fit into constrained environments. Takeaway, on software only MCUs, Ascons outperforms AES GSM in speed, energy, and memory footprints. Hence, it's ideal for IoT and wearables. On MCUs with accelerators, AES is faster and more compliant, though Ascon remains competitive in software. The strategy that can be taken is adapt a crypto agile model, use Ascon in constrained software only devices, and use AES in compliance heavy or hardware accelerated platforms. Bottom line, traditional cryptography remains essential for compliance heavy, hardware accelerated, and high throughput environments. Lightweight cryptography fills the critical gap for resource constrained devices, enabling stronger cryptography where AES or SHA would otherwise be impractical. The future is crypto agile. Organizations will need to support both and deploy each in context where they deliver the best balance of security, performance, and compliance. In summary, from an algorithm standardized perspective, Ascon AD128, it authenticates encryption with 128-bit keys. The Ascon hash 256, it's a 256 digest with 128-bit security. Do note, 256-bit digest with 128-bit security. The Ascon X of 128 and C X of 128 is our extendable output function. customizable for domain separations. It has a compact design, that is all functions share one 320-bit permutation, thus reducing the code size and RAM footprint compared to AES or SHA-3. It's efficient because it's optimized for software only implementation on microcontroller which has low energy use than AES GSM in devices without the AES hardware. From a assurance perspective, from security angle, the 128-bit strength in single user settings helps. Explicitly bounds for multi-user and nonce misuse cases. It has flexible truncation. Has implementation friendly, which is switches to little endian to align with the ARM platforms, pre-computation on options included. We'll go through these in some aspect later on. So Ascon does not replace AES SHA-3 universally. It's not going to replace it. Instead, it fills the efficiency gap in constrained environments where AES, CCM and SHA-3 are too heavy in a pure software environment perspective. Nonce. That's number used once. Nonce is a unique number used only once with a particular secret key. It doesn't need to be secret, but it must never be repeated under the same key. Analogy: imagine you are locking a safe every morning. To make sure today's safe key can't be confused with yesterday's, you attach a date sticker to the safe. The date isn't secret, everyone knows the date, but it ensures the key and the date combo is unique for that day. So, if you reuse yesterday's sticker, that is nonce, someone could break the system. Hence, in Ascon AEAD 128, the nonce is a 128-bit number you give along with the key to encrypt the data. It ensures each encryption looks different even if the message is the same. So that's nonce. Tag. A tag is like a digital seal or a stamp that proves the message wasn't changed. It generated by the encryption algorithm and sent along with the ciphertext. When the receiver decrypts, they also check the tag. If it doesn't match, it means the data was altered and the decryption is rejected. Analogy: when you send a parcel, you seal it with a tamper-proof tape. If someone tries to open or change the content, the seal will break and the receiver will know it's not authentic. The tag is that seal, a short piece of data that guarantees integrity. In Ascon's AEAD 128, the tag is normally 128-bit long, but can be shortened. But of course, the minimum is 32 bits. Shorter tags are like using weaker tapes. Still a seal, but easier to tamper with. I hope this helps with a better context on what tag is all about. In summary, nonce is a unique sticker to make each encryption different and secure, whereas a tag is a tamper-proof seal that guarantees the message was not modified. Now let's look at digest or digest. Digest is the fixed sized fingerprint that comes out of a hash function. For Ascon hash 256, the digest is 256 bit long. The longer the digest, lower are the chance of any accidental collision. Example, the message is hello. The digest would be 256 bit. It would look random. Now if you change one character, it would be a completely different digest. But do remember, it will still be 256 bit long. Now let's look at security level. We looked at digest, now we look at security. So when we say 128 bit security, we mean an attacker would need effort equivalent to trying 2 to the power of 128 operation to break in. That's an astronomically large, beyond the reach of any normal computer, in some cases even quantum for now. So 128 is means it is 2 to the power 128, that combination. So is 256 bit digest equal to 256 bit security? The answer is no. These two are different. A 256 bit digest is not equal to 256 bit security. Now, hash security is measured by the attack types. There could be collusion or pre-image resistance. When you say collusion, it is finding any two different message with the same digest. So for a 256 bit digest, say this would need 2 to the power 128 attempts. So collision resistance is 128 bit security. Given a digest, find a message that produce it. It would need about 2 to the power 56 attempts. Since that's the effective collision security and safe comparison baseline, SP 800-232 conservatively quote 128 bit. Analogy, think of digest like a huge lock with 256 pins. A lock with 256 pins. To open it by finding a matching duplicate key, you only need to try or 2 to the power of 128 keys. That's why it is called as 256 bit digest and a 128 bit security. In summary, the digest length, which is 256 bit, is the size of the fingerprint, and the security level is the practical strength, the effort an attacker must spend to break it by finding the collusion. Now let's look at a comparison. different Ascon families. The Ascon AED 128, it's used primarily for secure communication or messaging or transaction integrity, primarily around IoT device firmware updates or POS or point of sale encryption. So AEAD 128 primarily used in that space. Whereas the hash 256 Ascon family is used as digital signature or password hashing or data integrity, primarily around the medical records. When you go on to X of 128, it is used for long hash output or for a pseudo random bit stream generation or key derivations. But when it comes to CX of 128, it is similar to X of 128 plus multi-tenant or multi-service environment, which requires domain separations. Do note the hash 256 X of 128 and CX of 128, the bit rates are 64, capacity is 256 bits. So that's the capacity. The rate and capacity are similar. Whereas the AED 128, the bit rate is 128 and the capacity is 192 bits. You can pause the screen to look at the rest of the details. That should give you a perspective. So, Ascon AEAD 128. It provides both encryption and authentication in one operation. Encryption as well as authentication. The 128 bit strength, if full tag used, it truncates to a lower integrity strength proportionally. It has that security feature. Nonce masking is available to avoid multi-user security degradation. Nonce reuses weakness confidentiality to, though Ascon provides bounded resilience in misuse scenarios. So that's AEAD 128. When it comes to hash 256, it produces a 256 hash with 128 bit collision strength. It uses sponge construction with 64 bit. It's suitable for general purpose hash function, for integrity verification, digital signature, or password hashing. When it comes to X of 128, it can be used or it is used for key derivation, pseudo random stream generation, or anytime variable length digest are required, but it's limited to 128 bits. The Ascon CXOF 128, it is used for multi-service platforms like Telecom slice or BFSI tokenization schemes where different contexts must not collide cryptographically. When you say telecom slicing, this is one of the topics that I had created earlier on 5G slicing. You can look at that video, that might help you and get you a better context on the practical use of this. In summary, all four share the same permutation core, reducing software hardware footprints. The AED, the hash, and the 2XOF variants, they cover most cryptographic needs in a constrained device. The AES SHA remains mandatory in compliance heavy sectors, but Ascon enables strong crypto in places where AES or SHA are too heavy. Let's look at sectoral mapping. BFSI segment. Well, can be used in secure pin pads, point of sale terminal, handheld KYC verification devices, or mobile banking apps running on low power secure enclaves. It's also used in lightweight tokens for ATMs or branch authentication. Now, why is Ascon used? Well, smaller code footprints reduces the testing overheads in embedded systems. Strong AEAD ensures confidentiality and integrity of transactions without any AES acceleration requirement. It can complement AES GSM in hybrid fleets, ensuring crypto agility across point of sale and mobile devices. In telecom, it's used in 5G or 6G base station modules where you have a constrained hardware. It's also used in SIM or eSIM cryptographic operations. Used in lightweight secure signaling for IoT modules connected to telecom networks. Why? AED with low memory footprint suits the eSIM cards and embedded SIM controllers. The CXFO enables telecom operator to domain separate cryptographic material across multiple network slices or virtualized services. As mentioned earlier, there is a separate video on the 5G slicing. You can have a reference on that to get a better perspective on practical use of this. It supports secure boot and firmware validation for telecom edge devices. In IoT, well, it's used in smart meters, wearables, sensors in smart homes and industrial IoT. The constrained MCU based devices where AES hardware is unavailable is an excellent use case. Edge computing nodes requiring both secure communication and integrity checks is also a place where this is used. Why Ascon? Well, it is designed explicitly for constrained devices, for compact, energy efficient, single pass design. The hash and XOR functions allows firmware signing and authentication with minimum overheads. Streaming API enables processing of sensor data incrementally without large RAM buffers. From healthcare perspective, it is used in implantable medical devices, whether it is pacemaker or insulin pumps, or wearable health monitors and remote diagnostic devices. Used in telemedicine device transmitting sensitive patient data over low power links. Why Ascon? Well, it's energy efficient cryptography. It helps extended battery life of implantable and wearables. With a small code footprint, it simplifies regulatory validation and audit under the HIPAA or the ISO. The nonce masking ensures robustness in multi device healthcare ecosystems where nonce collision may occur. Bottom line, the AES SHA-3 remains mandatory in compliance heavy and hardware accelerated environments. The Ascon is the preferred option for constrained software only devices offering modern, secure, and efficient cryptography tailored for IoT, telecom edge, BFSI handhelds, and healthcare implants. Organizations should adopt a crypto agile stance, supporting both AES SHA and Ascon, and deploying each where it offers the best balance of security, compliance, and efficiency. So what each standard actually gives you? Well, the Ascon, the SP 800-232, it's a suite built around one 320 bit permutation. The Ascon AED 128 is a 128 bit key and 128 bit nonce or 128 bit tag. The Ascon 256 hash is a 256 bit digest. The XON 120, XOF 128 and CXOF 128 is a customizable XOF. That's the Ascon. Whereas the AES is a block cipher. The AEAD is achieved via modes like GCM. Whereas the SHA-3 is a hash. So why Ascon fits into tiny microcontrollers? Well, Ascon, well, one 320 bit state is arranged as 564 bit words. Hence, it's cheaper, linear diffusion is possible here. Comparatively, the SHA-3 is heavier. AES requires an additional MAC, adding compute and code in the software. The antennas and implementation perspective, SP 800-232 switches to Little Endian specifically to improve performance on Little Endian microcontroller and explicit node to embed targets. Ascon hash 256 has a rate of 64 bit with a capacity of 256 bit. It fits into tiny RAM and streaming. What guarantee you actually get? With Ascon AED 128, it's a single key nonce respecting the 128 bit security. There is no truncation. It provides multi key, that is, it's a 128 long bit unless you enable nonce masking, which restores the 128 bit without truncation. It supports the nonce misuse. Confidentiality can break on reuse, but the mode offers some resilience. Details and bounds are explicit. The total process per key is 2 to the power 54 bytes. From a truncation perspective, minimum tag is 32 bit. So there are strict decryption failure limits. These are very much specified. When it comes to Ascon hash 256 is approved hash. XOF is not approved as a hash function. Ascon XOF 128 and CXO412 are approved, whereas the XOF itself is not approved. The 128 and the CXO4 128 are. The GCM recommends a fixed 96 bit for interoperability. The SHA-3 security levels from the FIPS 202 applies. It's heavier than the Ascon. From a performance and code size perspective, it requires a smaller code size for Ascon. It adds the permutation core also means that smaller permutation core also means that it adds only about 12 to 16% to the code, whereas other add about 45 to 75%. its throughput is much better, and basically the software throughput. While the hardware acceleration flips the story, that is, if the AES has a hardware inbuilt, it's extremely fast and energy efficient. Ascon isn't yet an unambiguous or ambiguous in silicon, though tiny Ascon coprocessor do exist. But basically, when it comes to hardware acceleration, Ascon will not be able to match it at this point of time. Now comes to Cortex. Cortex is the brand name ARM uses for its family of CPUs. These are blueprints licensed by ARM to chip makers like whether it is STM Microelectronics and NXP, Qualcomm, Apple, etc. These are processor designs. They are widely used in microcontrollers, smartphones, tablets, servers, and embedded systems. There are few Cortex family, which is Cortex series, different needs. Cortex M microcontroller class, Cortex A application class, Cortex R real time class, Cortex X performance class. Cortex M is tiny, low power, cost efficient processor. It's found in IoT devices, wearable, medical implants, smart meters. This is where lightweight cryptography like Ascon matters the most. When you come to Cortex A, these are high performance core for smartphones and tablets and laptops. For IoT devices, you generally have Cortex M. For the smartphones, tablet, laptops, you generally would have Cortex A. It's found in Android devices, some Chromebooks, etc. When it comes to Cortex R, it is designed for safety, critical and real-time systems used in automotive control units, hard disk controller, 5G base stations. The Cortex X is top-end core for flagship smartphones and laptops. High-end phones, you'll have Cortex X, X1 or X3 series and so on. So why Cortex is mentioned in cryptographic discussion? Well, many IoT and embedded devices use Cortex M core. What's M? M, the one used in wearables. This one. So many IoT and embedded devices use Cortex M core, which are resource constrained, which means they have little memory, there are no hardware acceleration, battery powered. Ascon is optimized for these small processors where AES or SHA-3 may run too slowly without hardware support. Simple analogy, think of Cortex like a car engine family. The Cortex M is like a scooter or a small car or a light efficient built for small jobs. Cortex A is for like a sedan or a SUV, more powerful for heavy apps. Cortex R is like ambulance or racing car and must respond in real time. Whereas Cortex S is sports car, maximum performance, premium devices. I hope this example gives you a better perspective on what the Cortex series looks like. So Cortex is from an ARM family of CPU designs, powering everything from IoT sensors to smartphones and real-time controllers. So when NIST talks about Ascon being efficient on Cortex, they mean it runs well on tiny IoT class processors where there are limited resources. So from an energy and RAM perspective, Ascon 320 bit state, it has reduced RAM pressure and cycles used specifically on software only devices. From a compliance perspective, AES is approved from an Ascon is a NIST special publication. It's designed for conformant validation under the CAVP or CMVP like other algo. Ascon hash is approved as a hash but not for HMAC in this standard. XOF is not approved hash at this point of time. So when to pick what? Choose Ascon, AED or hash or XOF when there is no AES acceleration and care most about code size, RAM and battery, or you prefer a single permutation, or you need streaming, or your message volume per key fits the Ascon's 2 to the power 54 byte limit. That's where you choose your Ascon. Choose AES when your platform has a hardware or you need interoperability or compliance, or you require the vast ecosystem or require very high throughput. You choose SHA where a profile mandates SHA, or you need XOF output under the FIPS 202 for tiny MCUs, only when it is mandated. So let's go through a flow. How do you migrate if there is a requirement or a need? First is inventory hardware. Check for AES acceleration if present. Benchmark your AES GCM versus the software Ascon on your actual firmware. Then look at the security profile. If you need AED or hash, Ascon offers a compact pair with shared codes. Enforce nonce uniqueness for either Ascon or GCM, or use 96-bit IVs for GCMs when possible. Set conservative tag lengths. Document risk. Do perform your risk analysis. Respect failures. Then you move to key rotation and data caps. Rotate keys before hitting 2 to the power 54 bytes per key. References are there in the NIST publication, you can take that. The final is validation vector. Run your CAVP test vectors and keep implementation NDN correct. What are the constraints? Well, if it is pure software based on small MCUs, Ascon is usually the best to perform. Stick with AES GCM when you need strong compliance or high acceleration. Have a mixed fleet, support both. Prefer Ascon on tiny endpoints and AES where hardware exists to support you. The publication of NIST SP 800-232 marks a major milestone in the evaluation of modern cryptography. For decades, AES and SHA-3 have served as the backbone for secure systems worldwide, excelling in environments with abundant processing power, hardware accelerator, and strong compliance mandate. Yet, as the digital ecosystem expands into IoT sensors, medical implants, wearable, telecom edge devices, and embedded banking systems, these traditional algos often prove too resource intensive when deployed on a software only microcontrollers. The Ascon family, whether it is Ascon AE8128 or Ascon hash 256 or Ascon XOF 128 and the Ascon CXFO 128, fills this critical gap. Built on a compact sponge construction, With the 320-bit state, Ascon achieves 128-bit security strength, aligning with the modern cryptographic expectations. It achieves lightweight efficiency with small code size, with minimal RAM usage, and requires lower energy consumptions. It's flexible. It delivers AEAD, hashing, extendable output from a single design core. Its resilience, offering bounded protection in nonce misuse and multi-key scenarios. In practical terms, BFSI can secure the point of sale devices, its ATMs, mobile tokens in environments where hardware accelerators may not exist. Telecom can leverage Ascon for SIM and eSIM modules, secure signaling, and 5G edge controllers. The IoT ecosystem can finally adapt strong cryptography without sacrificing battery life or memory. Healthcare can embed robust security in wearable and implantables where energy and space are critical. At the same time, AES and SHA-3 remains indispensable in compliance heavy and accelerator rich environments such as data center, cloud and enterprise system. The path forward is therefore not replacement but crypto agility. Organizations must be prepared to deploy both traditional and lightweight algorithms in contexts where they perform best. Ascon fills the gap. To deliver modern cryptography where AES and SHA-3 are too resource heavy for IoT, healthcare, telecom edge, and embedded BFSI devices. From a lightweight and security perspective, the 128-bit strength with smaller code, lower RAM, and reduced energy use are ideal for software only microcontroller. It's versatile because it has AEAD, hash, and XOF variant built on compact sponge core, flexibility with minimal footprints. From a crypto agility, here is the key. The AES and SHA remains vital in compliance heavy, accelerator rich environment, while Ascon ensures security in constrained devices. In conclusion, NIST SP 800-232 is not just another standard. It is a strategic enabler for the next wave of secure, low power and connected technologies. By embracing Ascon, we ensure that security keeps pace with innovation, delivering trust, resilience, and efficiency at every layer of our increasingly constrained and interconnected digital world. With this, we have come to the end of this video. We covered the agenda as we have seen earlier when we started this video. I hope this has helped you in certain context to build a perspective around this space. I hope this helped you in your thought process. If you think this has brought some benefit to you and if you believe there are students or groups who might benefit from this, do share. We can pass the benefit to as many individuals as possible or groups as possible. With this, I conclude this video. This is your host, Savit Vitthal Salian thanking you. Namaskar.